Hello viewers, welcome to IGCSE Computer Science Boolean Logic Crash Course 2. In this tutorial, you shall be able to write a logic expression for a given logic circuit, complete a truth table for a given logic expression, write a logic expression for a given truth table, draw a logic circuit for a given truth table, and represent a problem statement. To write a logic expression for a given logic circuit, I have recommended 3 steps. And the first step is to identify all the intermediary logic gates in the circuit and write the expression for each. Step 2. Identify the logic gate that produces the final output. And the last step is to apply the rule relevant to the logic gate in step 2 to combine the expressions of the intermediary logic gates. Hence, you get the complete logic expression for the logic circuit. Let's take an example. The example requires you to write the logic expression for the given logic circuit. Looking at this, we have 3 different logic gates. The AND gate, which combines A and B, the NAND gate, which combines A and C, and of course, the OR gate, which combines the AND gate and the NAND gate. To address this problem, I have decomposed the gates into 3. The AND gate, the NAND gate, and of course the overall circuit where the AND gate and the NAND gate are combined using the OR gate. Hence, we get X equals A and B, or A NAND C. Let's go over to the next segment of this tutorial, and that is completing a truth table for a given logic expression. Again, I have 2 steps. And the first step is to identify the intermediary logic gates and label them. The second step is to represent the labels from step 1 and apply the Boolean logic rules to get the intermediary outputs and then the final outputs. An example is to complete the truth table for the logic statement. X equals A and B or not C, X or B not C. You have been given a truth table to complete, and we are going to address this as follows. The first thing we have to do is to allocate labels to the intermediary logic gates. And the first logic gate is A and B, which is given the label D. The second logic gate is not C, which is given the label E. And of course, combining the first logic gate and the second logic gate, which are D and E respectively, using the OR gate, gives us F. And further, we have B nor C, which gives us G. And finally, combining F and G gives us the entire combination, which is the output X. Moving on with these labels, D, which is of course A and B, reminds us of the rule of AND gate, which states that the output can only be true or 1 when both inputs are 1. We have 1 for both inputs in the last 2 rows of this table. Hence, D has 1 and 1 in the last 2 rows, and the rest are zeros. E is not C, and of course the rule of NOT gate states that the output becomes the reverse of the input. In that case, 0 becomes 1 and 1 becomes 0, and vice versa. So this is more like having 1 0 1 0 1 0 1 0, which is entirely the reverse of C. F is D or E. The rule of OR gate states that the output can only be 0 when both inputs are 0. Otherwise, we have 1. We have 3 occurrences of 0 as output for F because both D and E are zeros. These appear in row 2, row 4, and row 6, respectively. G is B nor C. The NOR gate is simply a reverse of the OR gate. In that case, the output becomes 1 only when both inputs are 0. The inputs we are considering here are B and C. Let's take a look at where we have B and C. In B and C, in the first row, are both zeros, hence we have 1. And there are also zeros in the 5th row, hence we have 1. The rest of the rows are zeros because we do not have both inputs to be 0. Moving on to the last column, which gives us the final output, X. We are combining F and G using the XOR gate. The rule of XOR gate states simply that the output can only be 0 when both inputs are similar. In that case, if both inputs are 1, the output is 0. Or if both inputs are zeros, then the output is also 0. Otherwise, we have the output to be 1. And this particular table reflects on the last column the XOR gate, which combines the inputs F and G. Moving on to the next segment, you shall be learning how to write a logic expression for a given truth table, and I have recommended 3 steps. The first step is to identify input combinations or rows with the output of 1. And the second step is for each row, combine the inputs with AND gates. And the last step is to combine rows with OR gates to get the final logic expression. Let's apply this using an example. The example here requires us to write the logic expression for the truth table. In this truth table, we have 4 different rows with the output of 1. How do we convert these rows? We are going to match each row with their individual expressions. And the first row is where we have A to be 0, and B is 1, and C is 0. Recall that the rule of AND gate states that the output can only be 1 when all the inputs are 1. Looking at this, A and C violate this rule. In order for us to enforce this rule, we need to convert A to 1 using the NOT gate, as well as C. And that is what we have just done. We are going to move on to combine this row with the next row below it, which has an output of 1, using the OR gate. And this happens to be the second step recommended above here. Now, again, we have B and C to be 0, and these 2 inputs violate the rule of AND gates. In that case, we need to convert these 2 inputs to 1 using the NOT gate. Moving on below it, we have B to be 0, and we need to convert this to 1 using the NOT gate. And finally, we have C in the last row where we have the output of 1 to be 0. Then we need to convert the C to 1 using the NOT gate. Hence, combining the entire rows where we have an output of 1, we have not A and B and not C, or A and not B and not C, or A and not B and not C and C, or A and B and not C. This is the final output for this truth table. So we have succeeded in writing a logic expression for a given truth table. The steps are the same, just apply them and it works for you. The next segment of this tutorial is to draw a logic circuit for a given truth table. And there are 4 steps that I have recommended. The first one is to identify input combinations or rows with the output of 1. The second step, for each row, combine the inputs with AND gates. The third step is to combine rows with OR gate to get the final logic expression. And the last step is to draw the logic circuit of the logic expression. Let's take an example. The table below has been given, and we are required to draw a logic circuit to represent this particular truth table. Our approach is going to be simple, and that is, first of all, to figure out what the logic expression would look like. And we have these going on here, where we have the first two rows to give us the output of 1, and we are going to combine each of those rows using AND gates. We have 0 for both inputs. To get a 1, these zeros must be converted to 1 using the NOT gate. And we have 0 for the first input A on the second row. We have to convert this to 1 using the NOT gate and combine the two rows using OR gates. We have applied these rules on our logic circuits, and this gives us not A and not B, or not A and B. This is our final logic circuit for the truth table given in this exercise. The next segment here is to represent a problem statement, and we have a typical example. I'm going to read out the wordings of this example. A wind turbine has a safety system which uses 3 inputs to a logic circuit. A certain combination of conditions results in an output X from the logic circuit being equal to 1. When the value of X is 1, then the wind turbine is shut down. The table on the right hand side shows which parameters are being monitored and form the 3 inputs to the logic circuits. The output X will have a value of 1 if any of the following combinations of conditions occur. Either turbine speed is less than or equal to 1000 rpm and bearing temperature greater than 80 degrees Celsius, or turbine speed is greater than 1000 rpm and wind velocity is greater than 120 kph, or bearing temperature is less than or equal to 80 degrees Celsius and wind velocity is greater than 120 kph. Design the logic circuits and complete the truth table to produce a value of X equals 1 when any of the 3 conditions above occur. To address this, take note of the content on this table. We have the parameter description, the parameter itself, the binary value, and the description of condition. The turbine, which is associated to the parameter S, is 0 when the turbine speed is 0 when it is less than or equal to 1000 rpm, and it is 1 when it is greater than 1000 rpm. T is 0 when it is less than or equal to 80 degrees Celsius, and 1 when it is greater than 80 degrees Celsius. W is 0 when it's less than or equal to 120 kph, and 1 when it is greater than 120 kph. With this in mind, let's move on. Now we have our rules, and we are going to painstakingly match them accordingly. Let's look at this. The first rule states turbine speed is less than or equal to 1000 rpm and bearing temperature is greater than 80 degrees Celsius. Our turbine speed is S, but when it is less than or equal to 1000 rpm, the bearing value is 0, which makes it to be not S. Our bearing speed T is greater than 80 degrees Celsius. When it is greater than 80 degrees Celsius, it is 1 in binary value, which makes it to be T. The next condition or rule is that turbine speed is greater than 1000 rpm. Our turbine speed S greater than 1000 rpm has the binary value 1, which makes it to be S. And the wind velocity is greater than 120 kph. The wind velocity greater than 120 kph has the binary value of 1, which makes it to be W. Hence, we have S and W. And the last rule is the bearing temperature is less than or equal to 80 degrees Celsius. When the bearing temperature is less than or equal to 80 degrees Celsius, the binary value is 0, which makes it to be not T. And wind velocity is greater than 120 degrees Celsius. When wind velocity is greater than 120 degrees Celsius, the binary value is 1, which makes it to be W. Hence, we have not T and W. Now, we are going to combine these rules using the OR gate. The individual rules, not S and T, or S and W, or not T and W. This is our logic expression for the given problem statement. And to represent the logic circuit, we are going to apply the rules of these logic expression and draw the symbols accordingly. Not S and T, which are given first, or S and W. Now you have S over here, and of course W, which is this, or not T. Now you have not T. This is not T and W. And the whole combination gives us the output of X. Don't worry if you don't get it right at first, but just study the pattern. And if this is your first time watching this particular logic problem statement, I would advise you locate the first tutorial on Boolean logic, that is Boolean logic crash course 1. So you get a formal introduction on this particular topic. That will give you a heads up, and that will help you to be able to digest this concept properly. Having said that, we move on to the closing part, where we have a challenge for you. If you really did this perfectly well, I would like you to take your time and work this out. Complete the truth table for the logic expression. So you have this logic expression. Your job is to complete the truth table. Feel free to expand the table, so you introduce intermediaries, intermediary labels for the various component logic gates. That will help you a lot in solving this problem. So I do not expect you to use a 4-column table. You can expand the table, but just reflect the output X, which is supposed to be the last column when you must have arranged all your labels properly. So at this point, we come to the end of this tutorial. I hope this helps you. And for those of you preparing to write your examination on IGCSE, I would encourage you to watch this over and over again. This will help you to properly understand the concept and to be able to solve more problem statements. I wish you all the best, and if you have not subscribed, kindly do so and click on the notification bell for more tutorials like this. Do well to also share with friends, because I believe that a successful one should be a success for all. If you're succeeding, make sure that people around you are also succeeding. Thanks for watching, and see you in my next video. Bye.